My name is Karen Daly and I teach mathematics at DKIT, a third level college in Ireland. This video was produced to further assist my first year computing students with their mathematical studies. At the end of this tutorial, you should have an understanding of how a computer represents positive and negative integers. Let's look at this first example. Find the 2-byte integer representation of 105. Now, 105 is the decimal number 105. It is an integer, and we want to represent this decimal integer using 2 bytes. The computer allocates 2 bytes to store this particular integer, and 2 bytes is equal to 2 multiplied by 8 bits. There are 8 bits in 1 byte. So that is 16 bits. 16 bits to a computer looks like this. It's like 16 little storage spaces, where each storage space stores either a 0 or a 1. So the computer is going to store my decimal number 105 as a binary number of length 16 bits. So what I have to do is I have to convert 105, the decimal number, to binary. Now you can do this on your calculator directly if you have a calculator that does these conversions for you. Alternatively, you can do it by hand by dividing 105 repeatedly by 2 and writing the remainder after each division, and then reading this remainder from the bottom upward, and you'll get your binary answer. There is a video on this, converting decimal to binary. The answer turns out to be that 105 is equal to 1101001 in binary. So try this yourself and make sure that you can do that conversion. The length of this binary number is 7 bits. We can count them: 1, 2, 3, 4, 5, 6, 7. But what the computer wants to do is it wants to represent 105 in 16 bits. So what it does, it fills out the bits with zeros. So before the number is stored, we've got a whole series of zeros. 9 of them in all, and then the number is stored as 1101001. So this here is my solution. This is the 2-byte or 16-bit integer representation of the decimal number 105. The next example. Find the 4-byte integer representation of the decimal number 23,467. Now, as we saw before, there are 8 bits in each byte, so 4 bytes is equal to 32 bits. I multiply 4 by 8 and I get 32. So just like we did in the previous example, to find that this representation, what we do is we convert this number 23,467 to binary. Now, unfortunately, we can't do this conversion directly on the calculator. The reason being that in binary, the number of zeros and ones that are needed to represent this number here are too many to fit across the screen of the calculator. So let me show you a way around this. What you should do is you should take 23,467 and on your calculator convert it to hexadecimal, base 16. And what you'll find is that 23,467 is equal to 5b A, B in base 16. Now, if I refer you to an earlier video again, converting between binary, octal and hexadecimal, you'll find that to convert from hexadecimal to binary, it's fairly straightforward. What we do is we replace each digit in the hexadecimal number by its 4-digit binary equivalent. So the binary representation of 5 is 101, so in 4 digits that's 0101. The 4-digit binary representation of B is 1011, of A is 1010, and B again is 1011. So that's the answer for 23,467. This decimal number in binary is equal to this. Now in this binary number again, how many bits do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different bits. And what we want to do is we want to represent the number using 32 bits. So just like before, 23,467 is equal to. So the computer representation of this is going to be, the first digits are going to be filled out with zeros. We already have 16 digits in it, so we need another 16 zeros before this number begins. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So there's my 16 zeros, and then I'm going to put in the number 0101, 1011, 1010, and 1011. So this here is the 32-bit or 4-byte computer representation of the decimal integer 23,467. Next example. Find the 2-byte integer representation of -234. Now, just like before, the computer is going to store this integer in 2 bytes, and 2 bytes is equal to 16 bits, 2 multiplied by 8. Now, a computer stores a negative number, in this case -234, using a method known as 2's complement. So we're going to look at what this is and how to implement this. So the first step is we're going to convert 234, the positive number 234, to binary. Alright, so you can do that directly on the calculator, and we'll discover that 234 is equal to 1110 1010 base 2. The next stage is to fill out the number of bits to 16 bits. So 234 is equal to, so I'm going to have 8 zeros leading, and then the number 110, 10, there's 3 ones there, sorry, 1010. Now the next stage of the 2's complement method is that I take this number and I flip the bits. So wherever there's a 0, I write a 1. So there's going to be 4 ones there, 4 ones there, then there's going to be 3 zeros and a 1, and there's a 0, 1, 0, 1. So that's flip the bits. And the last stage is that I add 1. So add a 1 in binary again. So 1 and 1 is 2, 2 is 0, carry 1. 1 and 0 is 1, so it's 1, 0, 1, 0, 0, 0, and then 1, 1, 1, 1, and 1, 1, 1, 1. And then this number here, that we've just after getting, is the 2-byte computer representation of -234. So let's recap. When we want to store a negative number, the computer employs what's called the 2's complement method. How it does this is that it takes the positive number, it converts it to binary, then it fills out the bits with 0 to the number of bits it needs to store the number in. Then the 2's complement method follows on by flipping the bits, turning zeros to ones and ones to zeros, and lastly adding 1. And the result that you get then after all these steps is the solution, how the negative number is stored on the computer. Now let's look at this example. Find the 4-byte integer representation of minus 101010. Now, just as we did before, 4 bytes, let's figure out how many bits that is. Well, it's 4 by 8, which is 32 bits. So we're going to have 32 bits in this number. So we're asked to represent a negative number minus 101010. It's a decimal number, so we employ again the 2's complement method. So just like before, we take positive 101010, this decimal number, and we convert it into binary. Now, unfortunately, again, this number is too big to convert to binary. Directly. So what we do is we take 101010 and we convert it to hexadecimal to begin with. So in hexadecimal, 101010 is equal to 18A92 base 16. And now we convert 18A92 base 16 to binary by replacing each digit by its 4-digit binary equivalent. So what we get is 1 is 0001, 8 is 1000 in binary, A is 1010 in binary, 9 is 1001 in binary, and lastly 2 in binary is 0010 in binary. So that's the binary representation of this decimal number here, 101010. Now next what we do is we have now to fill this number out to 32 bits. So fill. So there's going to be a whole series of zeros before this binary number. Now, how many digits do we have in the binary number? Well, we have 4, 8, 12, 16, we have 20. So we need 12 zeros coming before this number to give it its 32-bit representation. So 12 zeros, we'll try and fit them all in. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So there's my 12 zeros, and now the number. 1, 2, 3, 1, 1, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, and lastly 0, 0, 1, 0. So what's the next step? The next step is that we flip the bits. So we flip the bits, so we get 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, and lastly 1, 1, 0, 1. And then we add 1. So add 1. So plus 1. So put a line under it. And 1 and 1 is 2, so it's 0, carry 1. 1 and 0 is 1. So then it just continues on. 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 1, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, 1, 1, 1, and 1, 1, 1, 1. And what we have now here is the solution that I'm underlining in green. This is the 4-byte integer representation of the negative decimal number 101010. Now what I'd like you to do is to pause the video and try this exercise yourself. Find the 4-byte integer representation of these three numbers. Part A is the decimal number 1965 or 1965. B is the decimal number minus 2913. And C is a binary number, because you can see the little 2 written down here, and it's negative, and it's 101111. How did you get on? Well, here are the solutions to the various parts A, B, and C. So why don't you just pause the video for a moment and check your solutions against these and see did you get the correct answer. So let me briefly recap for you how we arrived at these solutions. So for part A, we wanted to represent the 4-byte integer representation of 1965. So remember again, 4 bytes is 32 bits. So your answer is always going to be 32 bits long. Now, how you do it is you take 1965 and you convert it to binary. And you have to go through hexadecimal for this because this number is too big to go directly to binary on your calculator. So to convert it to hexadecimal, it's 7AD base 16. And then if you want to go from hexadecimal to binary, you replace each digit by its 4-digit binary equivalent and you'll get 0, 1, 1, 1, 1, 0, 1, 0 and 1, 1, 0, 1. And that's the binary number for 1965. Then the last thing to get this answer here is you just fill out the bits to make it into 32 bits. Here you have 4, 4 and 4, so that's 12 bits. So you've ended up putting in 20 zeros here. Now for part B, let me change colour to orange just so that we don't confuse with the first one. Next one is a negative number. It's 2013. And what you do is you take the positive 2013 and convert it to binary via hex. 2013 in hexadecimal is 7DD base 16. And when you convert that to binary, what you get is 0111 1101 1101 base 2. So the next step is to fill this number here so that it has 32 bits in it. So you're going to end up putting, you've got 12 bits in it already, so you end up putting 20 zeros ahead of this number. So 0 all the way up to 0, so there's 20 of them. Right? There's 20 zeros there. And then we're repeating this number here. So 0111, 1101 and 1101. Okay, now that actually is the computer representation of the positive number 2013. But what we want is the negative number 2013. So what we have to do is we have to apply the 2's complement method to this. Right? If you apply the 2's complement method to this, what you have to do is flip the bits. So wherever there's a 0, you write a 1, and wherever there is a 1, you write a 0, and then add 1. So what you end up with is this answer here. And if you count all the number of zeros here, or ones here, there are 20 ones to begin with, and then there's these numbers here, and that's the answer. Now for the last part of the question, let me change colour again to a green this time. So what I want to do is I want the 4-byte integer representation of this binary number, which happens to be negative. So I already have it in binary form, and what I do is I take the positive binary number 101111, right, the positive binary number, and the first step is to fill it out to the 32 bits that I am going to represent it with. So fill it out, so end up having a whole string of zeros, and there happens to be 26 of them, 26 zeros. Before this number here begins 101111. Now I want the negative binary number, so what I have to do then is I have to apply the 2's complement method, right? And to apply the 2 complements method, what you do is you take this number, right, and you flip the bits and you add 1, right? So when you flip the bits, you can see you get a whole string of 1s, right? And then add 1, and this is the answer here. Now before we leave this exercise, can I point one thing out? The first bit in representing any number, so look at part A there, I'm putting a red box around the first bit. The first bit is known as the sign bit. So the first bit in any computer representation is known as the sign bit. And this bit, in this case here, for 1965, the value of the first bit is 0. And what that indicates is, if the first bit is 0, it indicates that the number is a positive number. So it's a positive number, right? And if you look at the next one, when we represented minus 2013, the first bit here was a 1, right? And if you see a 1 as the first bit in a number, it indicates that it's a negative number. Now this is only for the computer representation of the number, right? So let me recap that for you. So if the first bit in a computer representation of a number, the first bit is known as the sign bit. And if this bit is a 0, it indicates that the number it's representing is a positive number. And if this bit is a 1, then it indicates that the number that it's representing is a negative number, right? So you can see for part C as well, it was a negative number, so the first bit here was a 1, which is correct. It's a negative number. I've just picked up an error for these last 8 bits, they're wrong. The answer should read 1101 0001 instead of what was written here. So just correct that error, sorry for that. Now let's reverse what we have been doing. In this example, what we're asked to do is we're asked to find the decimal number represented by the 16-bit computer representation, and there are two parts, part A and part B. Let's look at the answer to part A first. First thing we have to do is to look at the first bit that's in the computer representation. And this first bit here, we identified it in the last example as the sign bit. And in this case, it's 0, and 0 indicates that it's a positive number, right? Now, if it is a positive number, all we have to do is we have to take the binary form of the number and convert it directly into decimal. So what we do is we take the binary part of the number, which is 11010, and we convert that directly to decimal using our calculator. And the answer turns out to be 26. So this whole string of numbers here, 16 of them, is actually the computer representation of the decimal number 26. Now let's look at the solution to part B of this question. Now part B, again, if we look at the first bit of the computer representation, it's a 0. And a 0 indicates that it is a positive number. It's a positive number, right? So the first bit being a 0 indicates that it's a positive number. So what we have to do is we have to take this number and we have to convert it back to decimal. Now, it turns out that this is quite a big number, and we're not going to be able to do it directly on the calculator. So just like before, we're going to go through hexadecimal. So I'm going to take this number and I'm going to convert it to hexadecimal. So we take the binary number and we group them into groups of 4, and that's the way the number is written originally anyway, so there should be no difficulty with that. We need to add zeros if we have to at the beginning of the number, but in this case we don't have to because it's filled out into groups of 4. And we just replace each group of 4 by its hexadecimal equivalent. So 10, that's going to be a 2. 1010, that's an A. 0111, that's a 7. And 4 ones, that's an F. So that's what that number there is equal to in hexadecimal. Now we want to convert this number here to decimal. So we can go to our calculator for this, put your calculator into hexadecimal mode, right? Enter these 4 digits onto the screen of your calculator, and then shift back second function into decimal mode, and what you'll find is in decimal this number is 10,879. So that's the answer, right? Part B. This computer representation that's given up here, the 16 bits, is actually a computer representation of the decimal integer 10,879. So let's do a similar example. Find the decimal number represented by the 16-bit computer representation A here and B here. So let's do A first. A. Alright. Again, the first thing you look at is the first bit. And in this case, you see that the first bit, which we call the sign bit, is actually equal to 1. And what that indicates, right, is that this number is a negative number. A negative number. So this computer representation is representing a negative decimal number. Now, if you recall, to represent a negative decimal number, we use a method called 2's complement. And so what we're going to have to do is we're going to have to reverse this method to get back to the original decimal number, right? The 2's complement method. And we can reverse the 2's complement method by applying the method again. So remember, the method was you take the original number, this is the 16-bit computer representation, you flip the bits, so flip them, and you get 0, 0, 0, 0, 4 zeros again, then 1 and 3 zeros, and then 4 zeros at the end, and you add 1. So add 1, add 1. Okay, let's add 1, then you get 1, 2, 3, 4, 1, 2, 3, 4, 1, 0, 0, 0, and then 0, 0, 0, 1. Next step is we take this number here and we convert it to a decimal number, and it's going to be a positive decimal number. Now, it's just this many digits you're going to have to enter, so you can do it directly on your calculator, and what you'll discover is that 1, 0, 0, 0, 0, 0, 0, 1 in base 2 is actually equal to 129, the positive number 129. So this is a negative number it's representing, so the solution to our problem is that this computer representation here, part A, is actually a representation of the decimal number minus 129. So that's the solution. Now let me move down the page to put in part B. Right, so let's enter in here, part B. So here is a 16-bit computer representation, and you want to find out what decimal number this represents. So again, just like before, the first digit of this is the sign bit, and that first digit is a 1, which indicates that it's a negative number. To store a negative decimal number, we use a method called 2's complement. And to reverse the 2's complement to get at the decimal number, we just apply 2's complement again. So what we do is we take this number and we flip the bits. So we're going to flip these bits. So you're going to have, where there's a 1, you put a 0, 1, 0, 0. Then we have 4 1s. Then we have 3 1s and a 0. And then we have a 0, 1, 0, 1. And then you add 1. Add 1. So let's do that. Adding 1 to this, you've got 1 and 1 is 0, and you carry 1. 1 and 0 is 1, so then you have 0, 1. Then you can just replicate these as they were before. There's no change to them. 0, 1, 0, 0. Now, again, this number here is now what we're going to have to take to convert to binary, to decimal, sorry. It's in binary form. And you can see that it's a very long series of zeros and ones. So you're not going to be able to do it directly on the calculator. So you're going to bring this to decimal, all right? And how you're going to do is you're going to do it via hexadecimal. So we're going to go to hexadecimal first. So the digits 0 are group them into groups of 4 as I have written them. And each set of 4 then we write down its hexadecimal equivalent. So 100 is the hexadecimal 4, 4 1s is the hexadecimal F, 110 is the hexadecimal E, and 110 here is the hexadecimal 6. So this is base 16. And now what we do is we want to convert that to decimal. All right. And to go directly to decimal, we can use the calculator. So put your calculator in hexadecimal mode and enter these 4 digits, and then do second function to decimal and see what you get. So the answer turns out to be 20,454. That's a positive number. Now remember that this is a representation of the negative number, so the solution to this problem is equal to minus 20,454. A computer is a finite machine. When storing an integer, we typically use one of three allocations. Short int is where the computer allocates 16 bits to the storage of an integer. Int is where the computer allocates 32 bits or 4 bytes to the storage of the integer. And lastly, long int is where the computer typically allocates 8 bytes or 64 bits to the storage of the integer. Now, each of these three allocations can store only a certain range of integers, depending on the number of bits allocated to the storage. It is important to be aware of the range of values a particular integer allocation has, as if you go outside this range, you generate what is called an overflow error. So let's try this example. How many integers can a 2-byte computer allocation store? And what is the range of these integer values? So 2 bytes is equal to 16 bits. And if you were to visualize what that might look like, it would be a register containing 16 different storage locations, and I've drawn them along here. Now, each storage location stores a 0 or a 1. So basically, we have two choices for each storage location. So the number of integers that can be stored is equal to 2 multiplied by 2 multiplied by 2 multiplied by 2 16 times, which is the same as saying 2 to the power of 16. Now we can work that out on the calculator, and what we get is 65,536. So a 2-byte computer allocation can store 65,536 different integer values. Now if we look at the range, this number here, 65,536 different integers, will be divided equally between positive and negative integers, right? So if we divide that by 2, divide 2 to the power of 16 by 2, we'll get 2 to the power of 15. So the range is going to start at minus 2 to the power of 15. That's going to be the smallest negative number that can be stored by this particular computer allocation. And it's going to go up to, right, the largest number, which is 2 to the power of 15. Now we're going to have to subtract 1 from this, because we have to take into consideration that 0 also has to be represented. So the subtract 1 will make 1 less a positive 1, because we have to take into consideration 0. So if we work this out in the calculator, the range is going to start at minus 32,768, and it's going to go up to 32,767. Now recall that the 2-byte computer representation was our short int, right? So if you allocate a short int to storing an integer, you can store any integer starting at minus 32,768 and going up to a maximum of 32,767. If you go to store any integer outside that range, so let's say you went to store 40,000 or minus 40,000, what you'd end up with is having an overflow error. So minus 32,768 is regarded as the most negative integer in the system, and plus 32,767 is regarded as the most positive integer in the system. Now what I'd like you to do is to pause the video and attempt these two exercises. First one is, how many integers can a 4-byte computer allocation store, and what is the range of these integer values? And the second exercise is to do exactly the same question for an 8-byte computer allocation. How did that go? Let me go through the solution with you. Well, the first thing is to note that 4 bytes, right, is your 32 bits. 32 bits. So the number of integers stored is going to be 2 to the power of 32. And you can work that out in the calculator. Obviously it's going to be quite a large number. And here it is here. Now if we look at the range is going to start at the most negative number, which is minus 2 to the power of 31. And it's going to go up to the most positive number, which is going to be 2 to the power of 31 minus 1. Again, you can take out your calculator and write down these two values, and they turn out to be these two values here, from this negative number up to this positive number here. Doing the same for the second exercise, we have 8 bytes, which is 64 bits. So the number of integers stored is going to be 2 to the power of 64, and that indeed is a big number, and the calculator will write it in scientific notation for you. It's 1.844674407 by 10 to the power of 19. Now looking at the range, the most negative number it will start at is minus 2 to the power of 63, and it will go up to minus 2 to the power of 63 minus 1. Again, take out your calculator, work out these two values, and what you'll get is, that should have been a positive there, so the range is minus this enormous number here up to 10 to the power of 18 is the magnitude, up to this number here, positive this.